All right, ladies and gentlemen, this is going to be your, it's not a lecture, I'm just going to work some sample problems for the type of problems that you will see in Section 5.3 and Section 5.4 for integrated rate law and half-life. Make sure you get out your, if you're having problems with these and watching this, you're probably having a problem with getting the graphing correct for the integrated rate law. So go ahead and take out your Kinetics 5.3 packet, and on that very first page, I'm looking at graphing with TI 83 and the integrated rate law. So I'll be walking through those steps, so make sure you have it out so you can follow along. And here we go. All right, so here's my problem. It has several steps. So for the reaction 2A, it gives me 2B plus C. The following data was collected. So I've got a series of things I've got to look at. Number one, it wants me to determine the rate law. In order to determine the rate law, I need to know the order of reaction. So I'm going to have to do that first. And then I'm going to have to calculate the K for the reaction, calculate initial concentration, and then what's some concentration after 70 minutes, and then it wants the half-life, and then essentially how long it'll take for the reaction to proceed to where there's only 13% of its original concentration. So a lot of information I need to go through here. I'm going to piece it up, and I have to realize that I'm going to have to go through this stuff pretty much sequentially, and it all starts with getting this stuff graphed and figuring out what's the order. So that's my very first thing I'm going to do, is I'm going to say, what is the order? All right. Now I can't just look directly at this because this is a concentration versus a time. It means it's an integrated rate law, and I actually have to graph this stuff to remember and to figure out what the order is with respect to reactant A. All right, so moving on. I'm going to do a couple of them at a time, all right? And so follow along, and here we go. Make sure you got your calculator out. Okay, so very first thing, to determine the rate law, I've got to figure out the order. And so I really want to know the order of A, right? And so the order of the reaction with respect to A, I need to figure that out. There's a couple of things that I know since I'm looking at a concentration versus time graph, and I know that, like, if I have the concentration of A versus time, if this is a straight line, then it is a zero order. If I have the natural log of the concentration of A versus time, I know that's a first order. And then if I have 1 over the concentration of A versus time, that's going to be a second order. And so I got to graph this stuff. And this is where most people get stuck, is they've got this pretty complicated set of instructions to use. But essentially I'm going to create lists for this stuff. And I'm going to have list 1, list 2, list 3, and list 4. My first list, this is going to be my time. So I'm actually going to put this into the calculator. My second list, this is going to be the concentration of A, or whatever reactant we're looking at. My third list is going to be the natural log of that concentration. And then the fourth list is going to be 1 over that concentration. And by making these lists, what that's going to allow me to do is actually put in this information and then graph it individually. All right, so here we go. I'm going to go ahead and pop up a calculator on the screen here. Follow through, because I'm going to go really fast. This video, if I insert it in here, takes up a lot of space, makes this video file size very large. So I'm going to be very sparing with the calculator, so be ready for this. So here we go. All right, so the very first thing I got to do, guys, I'm going to turn the calculator on, and I've got to clear all my lists. So essentially, if I look at my list, I'm editing my list. You see how I've got my numbers on my L1, L2, L3. So I've got to clear all those out. And so I'm going to go to Stat, and then I'm going to go to option number 4, which is Clear List. And then I'm going to start putting these in here. So L1, and then I'm going to hit the comma, which is right above 7, and then L2, and then comma again, and then L3, and then comma again, and then L4. And so I've got all my lists separated by commas, and all I do is hit enter, and notice how it says done. So now I have cleared my lists. All right, so now that I've got my list clear, guys, essentially what I'm going to do is I'm going to take a look at this concentration and this time. I'm going to stick it into the calculator, and they're always going to be in this order, right? L1 will always be time, L2 will always be concentration, L3 will always be a natural log of concentration, and L4 will always be went over that concentration. All right, so I'm going to run through this really fast, and again, I'm going to show you how to do it on the calculator, but it's going to be kind of a jump in, jump out, jump in, jump out kind of a deal. All right, so be ready for this. Here we go. Okay, so I've got my calculator. I'm going to go to Stat, and then I'm actually going to go to Edit, so I'm just going to go Stat and then Enter, and this brings me to my list. So notice I've got L1, L2, L3, L4. Well, L1 was my time, and so these were all separated by 10. So I'm going to do 10, 20, 30, 40, 50, and 60. And all I'm doing after I type in a number is I'm typing in Enter. And then L2 is going to be my concentration, so it's going to be 8.23 second E negative 3. 6.74 second E negative 3. Oop, I messed up on that one. So 6.74 second E negative 3. There we go. And then 5.52 second E negative 3. And then 4.52. And then 3.70. And 3.03. And then just double check that those are all correct, and they are. And so essentially I've got my list in, right? And then I'm going to go up to L3. So this time I'm not going to do natural log. I'm going to give it a function. So I'm going to do, notice I'm at L3. I'm not here, I'm at L3. And then I'm going to go natural log, and then second L2. And what I do is then that just tells me to do everything for L3, and notice it's populated my whole L3. I'm going to do the same thing for L4. I'm going to go 1 divided by second L2, so 1 divided by concentration, and hit enter, and it'll populate that out. All right. Okay, so now we've got our lists in there, guys. At this point, we can choose to do one of two things. We can either graph it and look and see if we can figure out the line, or what I like to do, I just like to go and look at the data. Because we have something called an R-square value. When we graph a line and we do a linear regression, and so this is a key word here, a linear regression. What this is, and this should be linear, not just lin. So a linear regression uses y equals mx plus b, so the equation of a straight line, and essentially it tells us how well the data fits. Right? So how well the data fits in that straight line. And the trueness or the correctness or the accuracy, if you want to think of it that way, is an R-squared value. And the R-squared value, essentially, the closer to 1, the straighter the line. So the closer the 1, the straighter the line. And so what I'm going to do is I'm going to go and I'm going to take these in pairs. And so I'm going to draw lines here just to keep this clear in your head. Is I'm going to do an L1 versus L2. And so when I do L1, L2, I'm checking for that 0 order. When I do an L1 versus L3, I'm checking for the first order. And then finally, when I do, let me get a different color ink here. When I do an L1 versus an L4, I'm checking to see if it is a second order. And so I'm going to do these three different combinations, and whichever one gives me my largest R-squared value, or the one closest to 1, that's going to be my straight line. That's going to be the order of reaction. All right, so I'm going to run through this really quickly, guys. So please keep up. I'm going to go ahead and pop the calculator back up here. All right. All right, so here we go. Let's go ahead and run these through. I'm going to hit Stat. And so I'm going to go to Stat, and I'm skipping, guys, steps 3 and 4. If y'all are following along on that piece of paper, I'm not drawing the graphs. I'm just doing the test. And so I actually want to go over to test, and I'm just going to scroll up because it takes less time. The linear regression TT test is closer to the bottom. I'm going to hit Enter, and then now what I'm looking for is my X list versus my Y. Well, my Y is what's going to change. Everything's going to be versus time, so that's L1. So I'm going to go and do L2 versus L1. I'm going to scroll down to calculate and hit enter. And what this is going to do is I'm going to be looking for my R-squared value. That's all I'm looking for to begin with. All right, so in this particular case, my R-squared value is 0.979. And so take my green pen, and this is 0.979. All right, and then I'm going to go to the next one. So stat, test, linear regression, and now instead of doing L1 versus L2, I'm going to do L1 versus L3, go down to calculate, hit enter, it's going to do it for me, and then I have another R squared value. Well, this one is actually 0.999, and then I have one more to do. Again, I'm going to go to stat, test, go up to linear regression, hit enter. I want to do L1 versus L4 now. Hit enter, and then look at the R square value, and it's 0.979 as well. So 0.979. So I'm going to go ahead and pause it. All right, so now we've gotten rid of the calculator, and we go back and we start looking at our data, and we say, well, which one actually fit best? And when we do that, we see that this is our winner, right? We had a 0.999 R squared value, which means it is actually closer to 1. It's the straightest line. And so this is going to be a first order reaction because of that. And when we do rate law, remember there's a difference between integrated rate law and rate law. So my rate law, if I'll draw it up here, is actually going to be, get a pen, is going to be my rate equals to my rate constant times the concentration of A, and I'm not going to put anything up there because it's first order, right? So the exponent is 1, and this is actually the answer to my problem. This is what it was trying to get me to, is what is the rate law? But to do that, I had to figure out what was the order of the reaction. All right, so we're going to go ahead and move on. All right, so now we're moving on, and this is, we want to actually calculate K, which is the rate constant, and we want to calculate the initial concentration. Well, if we look at my equation, I've got the natural log of A at some given time equals negative KT plus the natural log of A initially, right? And we know that this is a y equals mx plus b relationship, right? So I know that this is y equals mx plus b. I know these are the cases. Like this goes together, my x is my time, my slope is my rate constant, and then these guys are here. I'm just going to go ahead and warn you. The calculator, I don't know why it does this, but it does it. But it gives you into a y equals bx plus a. I don't know why it does that, but in the calculator what you'll see is that the b value it gives you is going to be your slope. The a value is going to be your y-intercept. All right, so just to keep you aware there, because what we're going to do now is we're going to go back in and look at this linear regression data that it gave us for our L1 versus L3 plot, and I'm going to go ahead and pause it, and I'm going to pull the calculator up, and I'm going to show you how to walk through that particular data to get the stuff out that you need, okay? All right, guys, so real quick, I'm going to go ahead and graph this again. So I'm going to go to stat, test, go up, linear regression t-test. See how it's L1, L4 here, so I'm going to do L1, L3. Hit calculate, and then I'm going to go and start looking through this stuff. Now, we're not going to get into most of this, but we're definitely interested in is this A value and the B value, right? Because remember, A is going to be my y-intercept, B is going to be my slope or my rate constant. And so I've got those there. You see them. And so again, just because the calculator takes up, in this video, takes up so much room, I see my A value as 4.60, my B value is 0.0199. I'm going to go ahead and write those down there, and I'm going to get rid of the calculator real fast. Just wanted you to see that on here, and the fact that they actually give it to you as the y equals bx plus a, right? And we went through that with what's down here. So hold on one second. All right, so I've gotten this information. It says calculate K for the reaction. There's nothing that I have to do to this, right? The slope of my line is my rate constant. I expect it to be negative because it's first order, so this is my rate constant, and the answer makes sense. For this one, where I calculate the initial concentration, this is where some people get mixed up, is that my y-intercept is actually the natural log of that concentration, not just the concentration itself. So I have to solve this a little bit. And I know from experience in my math experiences, to get rid of the natural log, I just raise it to the e power. So I'm going to raise both sides, and that's going to cancel that out. And so all I have to do is take this and I'm going to type it into the calculator, and it should end up looking like this. I'm going to do second natural log, which will bring up an E hat and open a parentheses. I'm going to put negative 4.60 in there and hit enter. And it's going to give me my concentration. I'm going to write it down here. All right, it's going to be 0.01005. And this is going to be my A naught. That's my initial concentration. And it's different for each of the three integrated rate laws, how you solve these. Just make sure that you understand what the y-intercept is. Because unless it's zero order is just the initial concentration, but for first order it's the reciprocal, right? So make sure that you're aware of that when you're solving these kinds of problems. Alright, so moving on, now I'm looking at what am I going to do if I want to calculate a concentration after some given amount of time, right? And so how do we infer that? How do we look at that? And we're going to use, since we know the order of the reaction, we're going to go back to our integrated rate law that the concentration at some given time, or the natural log of that concentration, is equal to the negative kT plus the natural log of A naught. Well, the beauty of this is that if you remember back from the last slide, we have this value. It gave it to us in the graph, so I'm going to get rid of that because I know that that's negative 4.60, right? I know my time, because it's given it to me here, is 70. I know my K value, and so all I do is I just plug this stuff in and I solve it. And so here we go. I've got, this is going to equal, I've got negative 0.01999 times 70 seconds plus negative 4.60. And remember, this is still equal to the natural log of AT. And so, hold on, I'm going to type this in the calculator and come back with a number for you. All right, so this is going to give me negative 5.999 and that's going to equal to the natural log of AT. And so again, don't forget guys, we've got this natural log here, and so to get rid of it, we've got to raise both sides to the E, and so that cancels out negative log, and so it just leaves me with my concentration at some time, and let me go ahead and type this in. So I'm hitting second natural log, and then this should be 0.00248, or another way to write that is 2.48 times 10 to the negative third. All right, and so it does make sense because that's less than the concentration that we had at 60 seconds in our graph, so we're good. Just don't forget, a lot of people miss this natural log stuff here at the end, and they just assume. You shouldn't have a concentration that's negative. If you're getting a concentration that's negative, you're probably doing something wrong, and we need to talk about it, okay? All right, here we go. Calculate the half-life of this reaction. A couple of things that I know. First off, I know my K value, and that's equal to negative 0.01999, and I write that down because the equation of half-life for a first-order reaction is just equal to 0.693 divided by K. Well, what you don't realize is that this negative value here has already been made positive when I changed all this stuff around. Because technically, when you go back to the derivation, this was a negative and this was a negative, but I know a negative divided by a negative is a positive. And so what people might also forget to do is I've got to make that a positive number when I plug this in. And so I end up with 0.693 divided by 0.01999. And then let me pause this and get you an answer here. Okay, so my half-life here is going to equal to 34.67 minutes. All right, so not too hard. Just we got to remember what the half-life equation is for first order. That's something that you're going to have to memorize. All right. In this last problem, it gets a little bit more complicated just because we're not going to a half-life, we're going to 13% of its original concentration, not 50, right? Something that people overlook is that your half-life is equal to 50% of the original concentration. And so let's take a look at how we derive this. And this is something that we went over in the notes, right? It's just the derivation of the half-life. And so from step to step, what we're going to do and really focus on is we're going to be focusing on this particular step right here. right? And more importantly, exactly where we got this half initial concentration, and it's because the half-life is half of the initial concentration. And so remember from the lecture that these initial concentrations calculate or cancel out, and so I'm just left with this, right? And so I end up taking the natural log of the percentage. This is essentially the natural log of the percentage that's left. And so what we do is we take a look at this and we say, well, we want to know how much time it takes to get to where we're 13%. Well, this is, as a decimal, is 0.13, right? 1/2 is actually 0.15, and so all I do is I'm taking essentially this and I'm solving with it, right? And so I'm going to come over here in the blue box here, and this is where I'm going to solve it out. So I'm going to take the natural log of 0.13 because I want 13%, not 50%. And that's going to equal negative KT. And then when I solve all this out, what we'll see is that you actually just end up with the time that it takes to get to 13% of the original concentration. So the natural log of 0.13 is actually equal to negative 2.04 is what it's going to be. And this is going to be equal to negative 0.01999 at that time. So take this and move it down, right? And so I end up with negative 2.04 divided by negative 0.01999. And this is what we were talking about in the last slide, that these negatives just cancel out, right? So they both end up being positives, and that's going to equal whatever time. So let me go ahead and divide this out here. And I end up with 102.1 minutes is going to equal my time. So it takes 102.1 minutes to get down to 13% of its original concentration. Big thing here to remember, guys, is just this is where we intercept this, right? We don't take it all the way to half-life. We take it here, and whatever percentage that we want to take it to, that's the number that we plug in, and then we solve it out just like we would any other math problem. All right, so make sure that you catch that, and if you didn't, listen to it again. Half-life is 50%. We wanted 13, so rather than putting a 0.5 here, we put a 0.13 because it's 13%. And hopefully this answers any of your questions. If it doesn't, post some stuff on Edmodo. Talk to your friends, and we'll see you when you get back.